Defining precision engineering today centers on the pursuit of extreme accuracy and repeatability, often measured at micron or even nanometer scales. This discipline is the bedrock of industries ranging from semiconductor manufacturing and aerospace to medical devices, where infinitesimal deviations can lead to catastrophic failures. Yet, the concept of precision is not a modern invention. Ancient civilizations, including those in India, demonstrated an astounding grasp of these principles, applying them in diverse fields. From the intricate carvings and exact alignments found in monumental temple architecture, such as the Brihadeswara temple, to the sophisticated metallurgical techniques used in crafting the Delhi iron pillar, and the highly accurate astronomical instruments like the Samrat Yantra, ancient Indians consistently achieved remarkable levels of dimensional control and functional accuracy. This early conceptualization and application of meticulous execution laid fundamental groundwork, illustrating that the drive for perfection and exactness is a deeply historical human endeavor. Our exploration will bridge these modern definitions with compelling historical evidence, showcasing the profound legacy of ancient Indian precision. The conventional historical narrative largely positions the Industrial Revolution, originating in Western Europe during the 18th century, as the definitive genesis of industrial precision. This era is widely credited with establishing the fundamental principles of modern manufacturing, including the development of standardized interchangeable parts and the advent of sophisticated machine tooling. Innovators of this period, often from Britain and later the United States, are frequently highlighted for their contributions to mechanical accuracy and mass production techniques. This perspective underscores a linear progression of technological advancement, asserting the preeminence of Western scientific and engineering endeavors in pioneering the meticulous accuracy and rigorous quality control that define industrial production today. For too long, the narrative of scientific and technological precision has predominantly focused on Western civilizations. However, a closer examination reveals India's profound and often unsung contributions that significantly predate or run parallel to these developments. Our first point highlights India's sophisticated metallurgy. The creation of Wootz steel, an ultra-high carbon crucible steel, was a technological marvel, renowned globally and forming the basis for legendary Damascus swords. Simultaneously, the Delhi iron pillar, erected over 1600 years ago, stands as a testament to unparalleled metallurgical purity and corrosion resistance, properties that eluded European metallurgists for centuries. Secondly, India's mathematical innovations laid the very groundwork for modern precise calculations. The invention of the decimal system and the revolutionary concept of zero transformed arithmetic and algebra, enabling complex equations vital for astronomy, engineering, and commerce worldwide. Furthermore, early advancements in trigonometry provided essential tools for precise measurements in fields from architecture to navigation. Finally, the ancient Indus Valley civilization showcased an astounding commitment to standardized measurement. Archaeological discoveries reveal remarkably uniform weights and measures used across vast regions, indicating a sophisticated understanding and application of metrology in urban planning, trade, and daily life, ensuring accuracy in an era often perceived as rudimentary. These examples underscore India's pivotal and often overlooked role in shaping the global landscape of precision, challenging us to reevaluate historical narratives. Ancient India cultivated an environment exceptionally conducive to pioneering advancements. Its landscape was dotted with meticulously planned urban centers, featuring sophisticated infrastructure such as advanced water management systems and robust public works, which underscored a deep understanding of engineering and urban planning. This foundational stability allowed for the flourishing of specialized knowledge systems. Significant strides were made in mathematics, with concepts like zero and the decimal system emerging, alongside profound contributions to astronomy, evident in precise calendrical calculations and celestial observations. Medical sciences, particularly Ayurveda, developed comprehensive diagnostic and therapeutic approaches. Furthermore, expansive trade networks facilitated not only economic prosperity, but also robust intellectual exchange across vast geographical regions, drawing in diverse ideas and fostering a crucible for innovation. This rich tapestry of organized society, profound intellectual pursuit, and vibrant cultural interchange established the essential preconditions for the unparalleled scientific and technological breakthroughs we will now explore. India's profound contribution to numerical precision is epitomized by two groundbreaking innovations: the concept of zero and the decimal place value system. The introduction of shunya, or zero, was not merely the addition of a new digit, it was a conceptual revolution. Zero provided a placeholder, enabling the development of finite systems to represent infinitely large numbers, a prerequisite for advanced arithmetic and algebra. Concurrently, the ingenious decimal place value system, also conceived in ancient India, offered an elegant and efficient method for numerical representation, where the position of a digit determines its value. These two interconnected advancements fundamentally transformed global mathematics, facilitating complex calculations that were previously impossible or exceedingly difficult. They provided the essential mathematical bedrock upon which future scientific and technological progress across civilizations would be built, marking a pivotal moment in human intellectual history. Ancient India's metallurgical prowess is profoundly demonstrated through its mastery of wootz steel, a crucible steel renowned for its exceptional hardness, pattern-welded appearance, and superior edge retention, which later inspired Damascus steel. This sophisticated material was meticulously produced by melting high-purity iron with carbonaceous materials in sealed clay crucibles, subjected to precise temperature control. Beyond wootz, Indian artisans exhibited advanced capabilities in large-scale iron production. A compelling example is the iconic Iron Pillar of Delhi, a colossal structure over 1,600 years old, which stands uncorroded to this day. Its construction signifies a deep understanding of metallurgy, encompassing techniques for large-scale forging and the development of rust-resistant alloys, capabilities that significantly surpassed contemporary global standards. This era represents a pinnacle of material science, showcasing an advanced, empirical knowledge of material properties and processing. Ancient Indian civilizations developed remarkably sophisticated and standardized measurement systems foundational to their advancements in science and engineering. Units such as the angula for length and the yojana for larger distances were not merely local conventions, but often established consistent benchmarks across diverse regions, ensuring uniformity in construction and trade. Precision was further enhanced by a range of innovative instruments. The gnomon, a simple yet effective shadow stick, was expertly employed for accurate timekeeping and determining celestial positions, critical for both calendrical purposes and astrological observations. Elaborate water clocks, or gati yantras, provided highly calibrated measurements of time. These refined systems extended to weight, volume, and even astronomical observations, utilizing precise scales, measuring vessels like the drona, and astronomical instruments for mapping the cosmos. The impact of these standardized units and instruments was profound, enabling the construction of intricate architectural marvels, facilitating highly organized urban planning in cities like Mohenjo-Daro and Harappa, and establishing equitable frameworks for commerce and resource distribution, underscoring a deep commitment to order and precision in ancient Indian society. Ancient India's commitment to astronomical precision is profoundly manifested in its sophisticated observatories. Structures such as the Jantar Mantar complexes, built from monumental masonry, were not merely buildings, but colossal scientific instruments designed for meticulous observation. These observatories facilitated remarkably accurate celestial mapping, enabling the precise tracking of stellar positions, planetary movements, and the establishment of coordinate systems. Beyond mapping, they were instrumental in highly accurate timekeeping, contributing significantly to calendar development and the prediction of astronomical events like eclipses. Their design reflects an advanced understanding of geometry, trigonometry, and spherical astronomy, underscoring a rich legacy of scientific inquiry and technological ingenuity. Ancient Indian civilization demonstrated unparalleled surgical ingenuity, evidenced by an extraordinary repertoire of medical instruments. Texts like the Sushruta Samhita meticulously describe over 100 distinct surgical tools, each designed for precise applications, ranging from incisions and excisions to bone setting and ocular procedures. These instruments, primarily fabricated from high-grade metals like bronze, iron, and early forms of steel, showcased advanced metallurgical knowledge and sophisticated engineering principles. Their designs were remarkably sophisticated, featuring ergonomic handles, sharp edges, and fine points, enabling delicate and intricate surgical interventions. This era's medical practitioners were not only skilled in their use, but also pioneered aseptic techniques, emphasizing the sterilization of these instruments. The meticulous craftsmanship and diverse functionality of these tools underscore the profound understanding of human anatomy and surgical requirements attained by ancient Indian physicians, laying foundational principles for modern surgical practices. Ancient Indian civilizations developed extraordinarily sophisticated hydraulic systems, demonstrating unparalleled precision in water management. This ingenuity is exemplified by the construction of intricate stepwells known as boweries, which functioned as multi-tiered reservoirs strategically designed to access and preserve groundwater. These structures showcased advanced hydrological understanding and meticulous stone masonry. Complementing these were extensive, precisely engineered canal networks, which efficiently diverted river waters over vast distances to nourish agricultural fields, ensuring consistent crop yields. Furthermore, the implementation of check dams and large-scale reservoirs regulated water flow, mitigating flood risks during monsoon seasons and providing vital reserves during droughts. This comprehensive approach to water resource management, integrating deep knowledge of hydrology, surveying, and civil engineering, underscores the profound technical acumen and foresight characteristic of ancient Indian societies, sustaining populations and fostering prosperity through millennia. Ancient Indian civilization's profound understanding of mathematics and engineering is vividly displayed in its architectural grandeur. Temples, far from being mere structures, were sophisticated monuments designed with astonishing geometric accuracy and cosmological alignments. Builders meticulously employed principles of sacred geometry, ensuring precise dimensions, perfect symmetry, and orientations that often correlated with celestial events. This precision is evident in the intricate carvings and the overall structural integrity of edifices like the towering vimanas and mandapas, where every element contributes to a harmonious whole based on rigorous mathematical ratios. Beyond individual structures, urban planning also exemplified this advanced precision. Ancient cities, such as those of the Indus Valley civilization, featured meticulously planned grid layouts with orthogonal streets, sophisticated drainage systems, and standardized brick sizes, indicating a highly organized and mathematically informed approach to urban design. These planned cities and geometrically perfect temples stand as enduring testaments to the unparalleled architectural and scientific acumen of ancient Indian societies. Ancient India's textile industry was a pinnacle of global craftsmanship, renowned particularly for its unparalleled excellence in fine muslins and dyeing precision. The legendary Dhaka Molmol, or woven air, exemplified this mastery, with fabrics so extraordinarily fine they were described as mist or running water. These transparent textiles were crafted from delicate hand-spun cotton, achieving a lightness and sheerness unmatched anywhere else in the world. Beyond the weave, Indian artisans demonstrated profound scientific understanding in their application of natural dyes. Vibrant hues derived from indigo, madder root, lac, and turmeric not only adorned these exquisite fabrics, but were also lauded for their remarkable color fastness, enduring through centuries. The processes involved complex mordanting techniques requiring precise knowledge of chemical reactions to bind the dyes permanently to the fibers. Furthermore, sophisticated methods such as resist dyeing and intricate block printing allowed for the creation of incredibly detailed and elaborate patterns. Techniques like kalamkari, where designs were meticulously hand-painted or block-printed using natural dyes, showcased an artistic and technical precision that was centuries ahead of its time. This fusion of delicate weaving, vibrant, lasting dyes, and intricate pattern work underscores India's enduring legacy as a world leader in textile artistry and innovation. Ancient India was a global leader in gemology, demonstrating profound knowledge in identifying, classifying, and sourcing precious stones from its famed diamond mines. This unparalleled understanding of material properties formed the bedrock for extraordinary ornate jewelry. Indian artisans employed sophisticated techniques such as kundan, meenakari, and intricate filigree, transforming raw materials into breathtaking works of art. The precision involved in cutting and setting diamonds, rubies, and emeralds ensured optimal brilliance and structural integrity. Each piece was a testament not only to aesthetic magnificence, but also to a scientific mastery of materials and an unwavering commitment to intricate craftsmanship. This legacy reflects an enduring standard of artistry and precision. Ancient Indian sculptors achieved unparalleled artistic precision in both stone and bronze. In stone, temple architecture and monumental rock-cut caves reveal intricate carvings that demonstrate exceptional mastery over material. From delicate filigree work on pillars to expressive deities adorned with elaborate jewelry, every detail reflects meticulous planning and execution. The precision extended to anatomical accuracy and dynamic poses, capturing a profound understanding of human and divine forms. Concurrently, bronze casting reached its zenith with techniques like the lost wax method or Sarah Purdue. This sophisticated process enabled the creation of iconic, perfectly proportioned deities such as the dancing Shiva, Nataraja from the Chola period. These bronze masterpieces exhibit a fluidity and balance that conveyed both divine power and artistic grace. Together, these sculptural traditions underscore a rich heritage of technical prowess and profound artistic expression, leaving an enduring legacy of beauty and spiritual depth. Ancient India's maritime engineering capabilities stand as a testament to its profound scientific and technical acumen. Our first point highlights a sophisticated understanding of hydrodynamics and naval architecture. Indian shipbuilders were not merely crafting simple vessels, they possessed an intricate knowledge of ship stability, buoyancy, and the dynamics of water, allowing them to design robust and stable ships capable of enduring demanding sea voyages. Secondly, advanced construction techniques were paramount. This included meticulous leak-proof joinery methods such as mortise and tenon, coupled with the strategic use of specialized timbers like teak and saul, known for their durability and resistance to decay. Iron reinforcement further enhanced structural integrity, ensuring these vessels could withstand the rigors of the open ocean. Finally, these precise engineering efforts culminated in the craft of large, ocean-worthy vessels. These magnificent ships facilitated extensive trade routes across the Indian Ocean and beyond, connecting civilizations and enabling long-distance exploration that significantly shaped ancient global commerce. This precision in design and execution underscores a legacy of unparalleled maritime engineering. The Iron Pillar of Delhi represents a pinnacle of ancient Indian metallurgy, providing a compelling case study for our discussion on enduring precision. Erected over 1,600 years ago, this monumental structure stands remarkably free of significant rust, defying centuries of environmental exposure. Its extraordinary corrosion resistance is attributed to a unique passive protective layer, identified as mesawite, an iron hydrogen phosphate hydrate that has formed naturally on its surface. Composed of approximately 99.72% pure wrought iron, the pillar's creation speaks to advanced iron extraction and forging techniques that predate modern industrial metallurgy by over a millennium. The ability of ancient Indian artisans to produce such high-purity iron, along with a sophisticated understanding of material properties that enabled its lasting integrity, continues to fascinate and challenge contemporary metallurgists and material scientists. The Iron Pillar is not merely an artifact, it is an enduring marvel, testament to an ancient civilization's profound mastery of material science. The question of why ancient Indian scientific and mathematical contributions have often been overlooked or undervalued is complex, stemming from several interlocking historical and systemic factors. Foremost among these are the profound colonial biases that shaped historical narratives. During centuries of colonial rule, there was a systematic effort to reframe history, often downplaying or omitting the achievements of indigenous cultures in favor of a Eurocentric perspective. This not only marginalized Indian contributions in official records, but also influenced educational systems globally. Secondly, a significant challenge was the lack of institutionalized preservation and accessibility. While many ancient Indian texts were meticulously maintained within specific lineages or religious institutions, a centralized, widespread system akin to modern libraries or archives accessible to a global academic community was not always present. This led to many valuable works remaining confined to smaller, localized circles, making their discovery and study by external scholars incredibly difficult. Lastly, persistent language barriers posed a substantial hurdle. A vast majority of these foundational texts were written in Sanskrit, a language often inaccessible to Western scholars. The scarcity of accurate and comprehensive translations further compounded this issue, creating an interpretive barrier that prevented broader understanding and recognition of the depth and breadth of Indian intellectual advancements. For too long, the narrative of global history has been shaped by a predominantly Eurocentric lens, often sidelining or minimizing the monumental contributions of ancient India. This slide, Reclaiming the Narrative, Integrating India's Legacy into Global History, addresses this imbalance directly. It advocates for a paradigm shift, urging us to challenge established historical frameworks and incorporate India's profound impact on world civilization. Ancient India was a crucible of innovation, pioneering advancements in mathematics with the invention of zero and the decimal system, in astronomy, in sophisticated medical practices, and in profound philosophical thought that influenced countless cultures. By showcasing these undeniable contributions, we aim to construct a more comprehensive and truthful global historical narrative. This integration is not merely an act of correction, but an imperative for understanding the true interconnectedness of human intellectual evolution. It enriches our collective understanding of humanity's past, presenting a more accurate and inclusive tapestry of global achievement. This segment delves into the enduring impact of ancient Indian precision, compelling us to rethink the conventional origins of engineering accuracy. Ancient Indian civilizations pioneered foundational principles essential for precision engineering, particularly evident in advanced metallurgy, sophisticated astronomical instrumentation, and intricate architectural designs. Their methodologies, characterized by meticulous measurement and detailed execution, were not isolated advancements, but became integral to a knowledge system that profoundly influenced subsequent global scientific and technological progress. Contemporary scholarship, through rigorous archaeological and textual analysis, increasingly necessitates a re-evaluation of established historical narratives regarding the genesis and evolution of precision. This reassessment recognizes ancient India's pivotal role, acknowledging their contributions as critical precursors to the advancements often solely attributed to later eras, thereby enriching our understanding of human ingenuity across civilizations.